living a very exciting times. We have observed what is called gravitational waves for the first time. And these gravitational waves have been emitted from binary black holes, and the collision of these. It's extremely difficult to solve Einstein's equations and to simulate these waves so we can learn about the systems. But you have for many, many years pioneered this field here. So can you tell us about how it all started?
It started from my youth, because when I was 14 or so, I was reading Einstein's papers. I even found a mistake in one of the papers of Einstein in the two-way problem. So when I arrived, after my thesis, when I arrived as a postdoc in Princeton, I went to the Institute for Advanced Study to meet the secretary of Einstein, because finally she handed me the manuscript of the unpublished computations of Einstein, Infeld and Hoffman on the two-body problem. I was already interested into that. So just to tell you that my interest in the two-body problem relativity dates from very long ago. And at that time, Joe Taylor announced the discovery of the binary pulsar, which is not made of two black holes but two neutron stars, which are nearly as compact as black holes. And the discovery of binary pulsars motivated actually to go beyond everything that had been computed before, to have a better description of the motion of two strongly self-gravitating objects, and in particular of the fact that because of the retarded wave interaction between the two bodies, they get closer and closer. It's called radiation reaction in physics. And in 1980, we were doing the first full computation of the radiation reaction at the leading order. And then at the end of the 80s and the 90s, the fact that the LIGO experiment in America, the Virgo in Europe, were starting plans to build really detectors of gravitational waves, it became more and more important to refine the theoretical calculation that we had been doing already for a few years.
So if I'm taking, a step out here, so the binary pulsar that you talked about here, you really have two compact neutron stars that are relatively far from each other. So we are not talking about two objects that are so close that they're merging, but still, when they're so far from each other, you see effects from Einstein's.
Not only effects from Einstein's theory, but effects from gravitational waves. Actually, the first proof that gravitational waves exist, are real, was obtained by comparing the binary pulsar observational data with the theory, particularly the one we had developed at the time, because in this system, the gravitational force between the two bodies takes a certain time to propagate. So here we don't need to talk about loss of energy and angular momentum in the form of waves, but the fact that there is a wave of the gravitational force being propagated from one body to the next changes Newton's law by a term opposite to the velocity, which is of the damping type. And this is what makes the bodies slow down on their orbit and then fall on a lower orbit where they go faster actually, and therefore the orbital period gets shorter and shorter, and this is observed with exquisite accuracy in many binary pulsars. So this agreement between the theory and the observation is a clear proof that gravitational wave exists, that gravity propagates at the speed of light. But although it is not the observation of waves in the wave zone, it is a proof that gravity propagates like a wave.
So then LIGO is really a detector now, you brought that up, a detector that has been under construction for many, many years. And that is a detector that is aimed at observation of the gravitational waves when the compact objects are getting so close they're about to merge, right? So it's a completely different regime.
Yes.
So when you're taking those equations that you talked about for calculating the orbits of the neutron stars and taking it all the way to the point where things start to get so close they're about to merge, you get into problems, right?
Yeah, if you use the usual things on which I worked a lot myself, which is an approximation by successive approximation, where you say, roughly speaking, that the force of interaction is Newton's force plus a correction which is v squared over c squared smaller, plus second correction plus third correction plus fourth correction. We could go to a very high order. The problem with this is that when two objects, neutron stars, but especially two black holes, are on the last orbits on which they can go around, all those successive approximations, they are of the same order of magnitude, which means the method that gives you the answer does not work anymore. That you cannot describe by using these approximate formulas what happens during the last orbit. And our American colleagues, like Kip Thorne, said, analytical methods will never be able to do that. We need numerical relativity. But in around 1999, 2000, numerical relativity did not exist and did not or could not solve the problem. It existed, but it failed in solving the problem. And it's only 5 years later that it gave the first solution. But with my postdoctoral student, Alessandra Buonanno, we used the previous calculations and we said, let's massage them, let's transform them in a form where we think they are able to describe now the last orbits, and not only what happens during the last orbits, but when the bodies, the two black holes touch, and when they merge. And we were lucky to predict for the first time the full waveform from infinite paths, when the bodies are very far away, up to the moment where after this in-spiraling motion they really merge, and then after merging, the black hole formed by the fusion of the two black holes is ringing, as we say, vibrate. So we wrote down this formula in 2000, and 5 years later, when numerical relativity could compute this, actually it agreed at modulo errors of 10%, you know, so we were 90% correct, okay? And in the years after this, as numerical relativity gave a better description of the merger, but not such a good accuracy for what is before, the idea was to combine analytical methods and some numerical results to have accurate description, which is still analytical in the sense you can fit parameters, change things, so it's very flexible from this point of view, that could describe the full waveform emitted by the coalescence of two black holes. And I was very happy when these waveforms computed this way by this so-called effective one-body method have been used for the first detections of gravitational waves by LIGO and Virgo.
So that's really plays an extremely important role right now, as they're having, you know, once you have the signal coming in from these binary black holes, you will need these, what you call the templates, to look for the signal, right? And also once you have the signal, you have to extract what are the masses, what are the spins of the black holes, and sitting and simulating that on a computer is extremely expensive, which can take months, years.
It takes something like 1 month for just 10 orbits.
So your work has really been pioneering the way that we can extract this information, even look for the signals. Is that a way to put it?
And I'm very glad about this, because as a theorist, you know, you work with equations, you say Einstein left us a beautiful theory, sometimes difficult to work with, but when you can extract from the theory new theoretical results that are useful and important for the detection of real objects in the universe, it's evidently the greatest pleasure a physicist can have in his life.